So there's going to be live demos that involve using DNS. So there's a precursor there. So this is kind of an important topic for me, mainly because I spent a lot of time thinking about what the future of ops looks like, right? So when I got into ops, the coolest thing you could do was like deploy a server, right, and configure it and harden it, get it ready for use, and write a bunch of Nagio scripts to babysit it. Turns out a lot of people are still doing that. And I think at some point something's got to give because that work isn't very exciting. How many people enjoy that kind of work? So, I mean, you can raise your hand. Like, if you like writing Nagio scripts, that could be your thing. It's okay. But I think as operations people, I don't think ops is just about managing servers of any kind, actually. I think it's one of those things that I would be happy if it went away. Someone will have to manage my machines, but I don't want that to be my full-time job. So thinking about if that world were to go away, and some people think that that's not possible, right? I'm not old enough to remember, but I saw on Wikipedia that there were people loading tapes into machines and punch cards. And I don't know anyone that does that job today. So there's a fair chance that some of the things we do today we won't be doing tomorrow. So this talk is about if we were to build using these new platforms, these new abstractions, so not command line, not ELF binaries, not servers and scripts, what kind of tools would we build, right? So I'm going to be using Kubernetes for this because Kubernetes presents a set of abstractions that allows me to really think differently about the tools I build. Now, it's not to say that you can't build tools like this without Kubernetes. It's just, I think it's much easier to build them when you have these set of abstractions. We're also going to talk a little bit about distributed systems, but not too much. Just enough to know what patterns we could use to build our own tools in this new world where things are all over the place. So I just want to set one really quick. How many people know about Kubernetes? Right, great. And for those that don't, I will do a 5-minute demo of what it is so we can all be on the same page. But at a very high level, Kubernetes is just a framework for building distributed platforms. So a lot of people do like to use Kubernetes directly, but it is quite low level. Some people will prefer to put something on top, things like OpenShift or Deis, which gives you like this Heroku-like experience on top of Kubernetes. So some people will build their own workflow on top. But Kubernetes was designed for that thing, right? We like to think of it as like the Linux kernel for your distributed systems, right? We take care of a lot of the underlying things that are hard, so you can actually just build and deploy apps on top. So I'm going to do a quick demo of what Kubernetes is because I need us all to be on the same page and understand a few things. So really quick, I'm just going to deploy Nginx because that's what you do when you talk about containers and clustered systems. So what I'm going to do really quick is just going to do kubectl run Nginx, and I'm going to give it a Docker image that I want to run. You guys all know that that's a real version number, right? This is not a version number. Don't do that. All right, so here's this image. So I want to tell Kubernetes I want to run this image, and I want a few copies. So I'm going to say, Kubernetes, I would like 5 copies of Nginx running. So what I'm going to do here is I'm not necessarily executing a script per se. I'm going to declare to the cluster that I would like it at some point between now and the future to get that running for me. It may never happen. There's many reasons why this may not ever work. That image may not exist on the Docker Hub. The system could be down. It could be partially available. It's all kind of things. So this is only my declaration. So I submit this to the cluster. What I'm hoping will happen is that my definition will get picked up and executed by the cluster, and I should have 5 Nginx containers running. So if I say kubectl get pods, so we put our containers inside pods, there's reasoning for that. So at this point, I have 5 of these things running, all right? Now, if I want to expose this to the public internet, all these things have their own dedicated IP addresses. So I need to be able to discover what are the IPs for this and automatically configure something like a load balancer, right? But I don't want to do that by hand. I don't want to actually build any tools. I don't want to install etcd or console. I don't do any of that. If the platform placed them, it should know where they are, right? So what I'm going to do is say, Kubernetes, I want you to expose these instances to the public internet. So I can say kubectl expose this deployment called Nginx, and I want to have you create a load balancer automatically for me, right? And then I want you to send traffic to port 80, right? So if I hit this, I'm going to ask the cluster to create a load balancer in my cloud provider, which is Google's cloud platform, and I want it to allocate a public IP address for me. This is what I'm asking it to do. So when I create that, let's look at what that declaration looks like. So for instance, this image, this deployment that created all 5 of these, what does that declaration actually look like in the system? So kubectl describe deployments, or actually let's do it this way, kubectl get deployments nginx-o. I just want to see this output as YAML. So here's what we actually declared in the cluster. So some of this is metadata that gets put in there automatically. But we gave the cluster this definition. We wanted it to do a deployment. We wanted to have 5 copies of it. We wanted to use this template below. Actually, we have a rolling update strategy. So if I ever want to do a rolling update on the version, here's how that should actually work. So if I change the image version, that should automatically work. I also want to run a particular set of containers. And in order to spit those containers out, I want to use this template. So what this template says is use this specific container image. That's the one that we typed in the command line. There's a couple of other things here that are probably not that important, but the key things here is I want to run this image. I want 5 copies of them. And if you ever need to do a rolling update, here's how you do it, right? So while that's finishing, let's see if our service is available. All right, so now we have this service. Now, the key thing about this is that I declared that it should expose the deployment. So it should go read the deployment and figure out how to find all the containers in that deployment. Let's say kubectl describe, let's say service nginx. You notice here that it found all 5 of these, right? So it was able to do that by some label queries. I won't go into too much detail here. But if I add or remove containers to this backend, this will automatically populate. So there's 5. Scale deployment nginx replicas equals 3. All right. So as soon as I do that, the system should respond to my request. We describe this again. And see now we only have 3. So I don't need to manage that at all. Kubernetes will take care of that for me. I declare what I want. Kubernetes makes it so. Then what we can do is, once we have this public IP address, I can actually start to interact with my particular workload. All right, so we have 3 of those running. So I'm going to grab this public IP, and we're going to hit it with curl, just to make sure it works. So we hit this, and we see that we have nginx running. Great. Let's verify the version really quick. Right, so that's not a proper command, but I do see that it spits out this version for me. So the last thing we're going to do is do grep. I just want to print out this nginx thing every time. Let's make sure that that works. It does. So let's say while true, do troll. That's a new keyword. I just invented it for you guys. All right, -s to make that silent. We're going to grep this out, and then we're going to sleep for a second or half a second. All right, and then we'll be done. Okay. So we see that this is version 1.10. Whatever. All right. So now I'm going to declare that we want a new version and see if that declared state can actually help us. So I'm going to say kubectl edit the deployment for nginx. So I'm going to edit this state. So I'm telling the cluster manager, give me the current state of my deployment. We see we're at revision 1. So what I want to do now is tell it that I would like a different image in place. That's the only thing I'm going to change here. All right, so I'm going to change. Let me make sure that I didn't type anything weird. Okay, so we're going to change the image. I think the next version that's available is 1.11. So I'm just going to save that. And then what I expect my system to do is automatically make that so. And we see that the rolling update happens, right? I don't need to find the nodes. I don't need to log on servers. This is just what Kubernetes does. And it's pretty responsive. And we're going to see when we dive deep into the details why it's responsive. We're not doing 30-minute intervals or check loops, right? So that's how Kubernetes works at a high level. But that's deployments. We all get deployments. Putting bits on servers, to me, that's not very interesting. So let's delete this deployment and talk about building our own tools on top of Kubernetes. So kubectl, I'm just going to delete the deployment. Let's get it off my system. You also notice here we're not talking about nodes. We don't log on to servers. We don't babysit the servers. That's not what our goal is. Our goal is to focus on the application. All right, so let's talk about other things we can do in Kubernetes. So the main thing that you have to understand when we're building this new set of systems, you can count on global cluster state. So as a sysadmin, when I built tools traditionally, it's like you have to go to all the servers in the infrastructure and gather a bunch of data. or figure out how to extract data from every server in the infrastructure and group it somewhere so you can rely on it. So even though that works, we always have a consistency problem. Most people do not have any consistency in some of their environments. So you're pulling state from some nodes. Maybe you have it all, maybe you don't. Maybe your tool runs and thinks it has a partial view of the cluster. Maybe it does, or maybe it doesn't. So to make Kubernetes work, we rely on global cluster state. Now we store all of this in etcd, and we're guaranteed to have some consistency because we have a consistency protocol that we use called Raft. So as servers or as clients report state into the cluster, you can guarantee to look in one place and get an agreed upon state across the cluster. The next thing is these controllers. So this idea that everything is decoupled. None of the components inside of Kubernetes talk to each other. When I was creating those workloads, they were put on the nodes by a scheduler, but the scheduler never talks to any of the nodes directly. It just upstates the state that says you should be running this, okay? The next thing is the scheduler. So this idea of where do I place my particular workload? How do people do this today? Like spreadsheet-driven operations, right? Even if you have fancy automation tools, you still have some authoritative list of this app goes on this server, right? And that has to change in order to make some of these things work. And also, most of the schedulers that we get out of the box are very generic. They're good at saying CPU memory requirements. They may support custom metrics. But what if your business wants to do something like, hey, run this on the cheapest node in my infrastructure? Most of these schedulers have no concept of that. You're going to have to add your own metadata and use that metadata to make scheduling decisions. And we're going to see what that looks like today. The other thing is we talked about earlier is consensus. We need to make sure that when we're looking for things that change in our infrastructure, that everyone else agrees on the same thing happening, right? Because you can get into weird states if this is not the case. We'd also talk about the watch pattern, right? So I come from the configuration management world where you kind of set a interval loop. Your configuration management of choice will just loop over iterations. The problem with that, though, is the latency is too high, right? It works if you have 50 servers, 100 servers. But what if I have 10,000 servers, right? We don't want to sit there waiting for this timeout to expire. You can lower that. You can lower those intervals, but the problem is you start to get the thundering herd problem, right? Where everything goes into the server and tries to pull things, even when there's nothing to do. So what we want to do is leverage a watch pattern to only grab data when there's an event that needs to happen. The other important thing is the control loop, right? This idea that we're watching for things doesn't mean we're always going to see everything, right? We may drop things on the floor. We actually may start our watch, and the history of changes rolls off that we won't be able to get it. This is a common distributed systems problem. And to solve that, we can always have a reconciliation loop that can go back and make sure that we're in sync with the rest of the cluster, right? So we're going to see all of these things in action to build common tools, right? So we need use cases, right? You just don't build tools for the sake of building tools. So the first use case I'm going to have is I need to secure my HTTP endpoints with a TLS certificate, right? If you spend any time in ops, especially before Let's Encrypt, this is a very painful process, right? Someone generates a CSR, you pay tons of money to some CA. You don't know why you're paying the money, but you have to pay the money. They give you this cert back, and then someone needs to track when it expires. This is completely painful, right? Many companies run into issues where it expires and no one knows about it. Your customer tells you that your cert expired, and you have to go renew it. So what we want to do is leverage some better tools. One, we would do Let's Encrypt, but also how would we integrate Let's Encrypt into a system like Kubernetes using some of the principles that we talked about. So we're not going to be in this world of writing scripts. So one idea would be I could just write a bunch of shell scripts and put the shell scripts on the servers. But then the next question is, well, what server should have the shell script? Well, only the ones running the web server. Well, which ones are running the web server? Well, these 5. But what happens when those 5 die? Well, then these other ones, and then too much work. What we want to do is declare to the system that the certs must be there, and anything that needs to use the cert should just declare that they want to use the certs. And that way we don't pin ourselves to individual machines. And this is critical to build some of these what I consider next generation tools. We have to decouple ourselves from the node. Right now, all of our tools are very node centric. They assume you're going to do a deployment to a node. We have to remove that. So we're going to build this thing called Coop Cert Manager. This code's on GitHub. I'll share links later. But let's look at how this thing is built. Some people like diagrams, so I made diagrams. I don't normally do diagrams, but these diagrams are for people that like diagrams. So what we need to do is build a system like the one we saw earlier. A user or some system will create certificate requests that go into the Kubernetes API. Now, this would be the authoritative place that we store the declaration for a certificate. Now, once that is in place, we'll have our certificate manager watch the Kubernetes API for certificate objects, meaning someone would like us to create a certificate and keep it renewed on their behalf. That's all we want the user to do. This isn't infrastructure for code. You're not going to give me any scripts. You're not going to give me any DSL. I just want to know what it is you want me to do. Once I have that declaration, my job in the certificate manager is to extract away what it means for asking for a cert and getting one. Here, I'll do some orchestration using Let's Encrypt. If you're not familiar with the Acme protocol, Let's Encrypt, I can actually give it a request for a certificate by domain name and tell it what challenges I can accept. The challenge that I'm going to accept for this particular talk is I'm going to put a DNS record showing that I own the domain, and then it will validate that that token is in place, and then it will issue a cert because it knows that I own the domain. Only the person that owns the domain should be able to create DNS records inside of the DNS server that's authoritative for that domain. Once that happens, I'll take the cert that I get from Let's Encrypt, and I'll store it in the Kubernetes API. I don't even know who the consumer is, but that's all the declaration told me. If anyone wants to use that certificate, they should also perform a watch to see if the cert shows up or if the cert ever changes. And these things are going to be decoupled so we can all work in an asynchronous way. And also, I can take things down without affecting any part of the system. At a high level, the code for this, I'm not going to show a lot of code, but at a high level, the code for this kind of looks like this. I'm going to process a certificate from a certificate object. Once I grab that certificate object, I'm going to create an account. So I'm throwing away some of the error handling so it can fit on a single slide. I'm going to create an account using my email address that's found inside of that certificate object. I'm going to get a challenge from Let's Encrypt. Once I get that challenge, my goal will be to create a text record based on that domain and that challenge. And then I'll accept the challenge. So meaning, once I create this DNS record, it's my job to ensure that that text record is in place. If it's in place, I will accept the challenge, and then Let's Encrypt will go and verify that that DNS record exists, and then it will issue me a certificate. So here we're getting our certificate. Once I have that certificate, my job is to sync the Kubernetes secrets object. So Kubernetes knows nothing about Let's Encrypt. That's my tool's job, right? So now, once we have that, we want to be able to watch for certificate changes. I don't know whenever a cert's going to show up. So we're going to use the watch pattern here. So this is a little bit of concurrency that we're doing in Golang. I have a function that will call a watch against the Kubernetes API and sit there and block until a certificate shows up. Once that certificate shows up, the certificate will be placed on a channel. And here I'm just selecting over either I'm going to get some errors that I need to print out, or I'm going to get some certificates that need to be processed. But this will only fire when that certificate is actually ready. So we won't be polling unnecessarily against our API server. So this watch pattern is going to be key to make this work and seem responsive. So let's do a demo of this thing. All right, so the first thing we need to do is we don't have support for certificate objects. So kubectl get certificates. Right, there's no such thing as certificates. Kubernetes doesn't even know what that is. Now, if you're used to most plugin systems, you would have to write some code and rebuild the thing, and then it will understand what certificates are. So what we've done in Kubernetes is we made it really simple for you to extend it. So if you give me an object describing what your thing should be, we will automatically create a REST API for you and handle the storage. The only thing you need to do is basically watch for these things to be created and create them. So let's look at one of these extensions. So here's a certificate extension. So this is very simple. I'm not actually using a schema here. I'm just saying this is a third-party resource. I'm giving it an API version. And here's the name of my resource. So it's a certificate stable Hightower. That's my namespace for all of my extensions. And this is going to be version 1 of this. So I'm going to give this to the cluster to declare that I want it to now handle all of the things that it takes to manage state for this new object type. Okay? So let's add this to the cluster. kubectl create -f extensions certificates. So at this point, I now have a REST API, and I also have storage and all of the things that come with that built in by default for me. So at this point, I can start creating certificates. But now let's launch the thing that will actually process the certificates. So we saw a high level of the code. So let's look at a deployment for our kube cert manager. So our kube cert manager, its job is to, so there's multiple things happening here. I'm only going to run one copy of it. But my cert manager actually handles state. So we have volumes here. I'm going to persist the certificates that I get back from Let's Encrypt. So this is kind of like any microservice pattern that you'll see. I own the certificate data, not Kubernetes. I'm the source of truth. And we'll see why that's important in a moment. So we take this volume, and I'm going to mount it in a place that when I create my database from my application, that I can actually write here and have it persistent in case my container gets deleted and needs to come back. So we can actually do stateful things. Here, I'm just going to use the staging website for Let's Encrypt. And I'm going to do 10-second sync intervals for my reconciliation loop to make sure that any secrets I create stay there. So this is it. So we're just going to deploy this thing. I'm going to talk about the significance of this other container. This is the kubectl proxy container, and we'll talk about that later when I do the scheduler demo. So we're going to create this and deploy our own controller manager here. So let's deploy it. So create -f deployments kube cert manager. All right, so once this is deployed, we now have this new service. Let's see how long it takes to get up and running. All right, so it's creating now. So what's happening is we're getting a volume attached to whatever server the scheduler placed it on. We're creating the container. And at this point, when this is done, we'll be able to start creating certificate requests. So we'll let that finish. The next thing we need to do is actually create a certificate object. So this is what these things look like now. So here's a certificate object. I'm able to create these now because I created the extension inside of Kubernetes previously. Here's the name of my certificate object. So this is going to be a real certificate that we're going to grab. We're going to do it for the hightowerlabs.com domain. I need an email address for Let's Encrypt so I can register. I also made this thing pluggable so you can actually add new DNS providers. I'm just going to use the Google provider that's built in. I'm also going to talk about the secrets required for this provider. So here is a secret object that will have all the credentials needed by that provider. Okay. So let's make sure this thing is deployed. All right, so let's look at the secret to make sure that I actually have this service account in place. All right, so here's my service account for Hightower Labs, but you'll notice we don't have any TLS certificate secrets in place, and that's our job now is to create them. So I'm going to create the certificate object. I'm going to do this in a separate window so we can actually see the logs from our actual cert manager. So kubectl logs, and then we're going to view the logs remotely for this particular tool. And then we'll just tell the logs here. All right, so we see what's going on here. I'm starting my certificate manager. It started successfully. And I'm doing retries against my Kubernetes API because my proxy starts in random order. So there's no guarantee that it's going to come up first, and I assume it can fail. All I do is print the failure and try again. So everything is up now. I'm watching for certificate events, and I'm also going to do that reconciliation loop to make sure that everything is in sync in the background in case I drop any of the watches on the floor. So let's just leave that running. So now it's time to create a certificate. So kubectl-f, create the certificate object, and we're going to enter it to the system. And as soon as I do that, this thing picks it up, right? Because of that watch pattern. As soon as the API server gets consensus from its backend etcd store that that certificate is firmly in place, everybody else will be notified that it's watching it. Now, once we have this, we're actually going out to Let's Encrypt. We've created an account against their servers. They gave me back my challenge token. This is the token that I put into my DNS server. And what I'm doing now is querying my authoritative name servers just to make sure that it's actually in place. And we can actually go here and hit refresh. And this is my Google Cloud account. And we'll see my token. So there it is. So this is pretty much a public token. So if that token matches what Let's Encrypt is expecting, they'll actually issue me a cert. Okay? So I'm making sure DNS is propagated now by checking the authoritative name server. So here's my 4 authoritative name servers for that domain. I'm querying them just to make sure that that record checks out. I'll sleep for a while to make sure that the TTL expires, and then when Let's Encrypt goes to verify, it'll work, right? So I'm doing this to make sure that it works every time. So once this is complete, we'll see that the DNS propagation is done. I'm going to tell Let's Encrypt, hey, I'm done. It validates it. It gives me a certificate back, and then it updates the Kubernetes secret because I declared that the secret should be there. So if I come over here now and say kubectl get secrets, we see that we now have the secret in place, right? And it's declarative. So what happens if I delete the secret? So if I say kubectl delete secret, and we're going to delete this hightowerlabs.com secret, we never changed the definition. We never said that the secret should not persist in Kubernetes. So what will happen is our manager will find this and say, hey, I got to sync this. It found it missing. It's going to put it back. And since the reason why I'm authoritative for the cert and not Kubernetes is because people could delete it from Kubernetes. But like a good microservice pattern, I own the certificate data. I can just put it back. I don't need to go get a new cert from Let's Encrypt because that cert is still valid, right? So it's a good pattern to make sure that when you build these tools, most of the time the data belongs to you. Do not propagate it to another system because you won't be able to do things like this if you do. So if I do a get secrets now, we see that it's put back, right? So this is great. It protects us from other issues. Now, how do we consume the secret? So once the secret's in place, I won't go too deep into this, but once the secret is in place, you can consume it. So this thing called dynamic certs, all it does is it's a little hello world app. It will read its certificates from the file system. But the thing that's special about this app, it will use IF notify to tell it whenever the secrets change. So it will watch its own file system. And if I ever have to renew a cert, all I have to do is update the secret. The kubelet will update the file system of every process running this particular application, and they will all reload their secrets or their certs automatically. And the next HTTP request will get the new certificate. There's no management needing to be done here. So let's deploy this app, and we'll actually see how this works. So kubectl, or Dynamic Certs 1.0, we're going to get our certificates from the file system. Our certificate is going to come from a secret named Hightower Labs, right? So it doesn't know how it got there. I could do it manually, put the cert in place, but Let's Encrypt is doing this in the background, but my app doesn't need to know about Let's Encrypt at all. It just needs to know the thing it's been doing, grab your certs from the disk. So let's create this thing and see what happens. So kubectl, create-f, deployments, dynamic certificates. So at this point, we now have this thing launching. It's going to pull the certificates from the file system. If everything works, we should be able to hit it. So it's actually running already. So now let's verify that it actually works. So ahead of time, get svc. I have a public IP address for this. So let's see if we actually have a real certificate. Okay. So this is from the staging server, so I doubt it will actually be trusted by this particular browser. All right, so if you ever see this lock when you're logging into your bank account, it's fine. Keep going. Don't worry about it. So we're going to proceed to it. Don't do that in real life. But we'll look at the information about the certificate. So we'll get the details, and we see that this thing is probably small here, but it's a fake LE certificate because we got it from Let's Encrypt. But this was issued by Let's Encrypt. And one thing we can also do to make it a little bit clearer, I'm going to get the actual serial number for the cert, and we'll see what happens. All right, so we have that. So now we'll do OpenSSL, and we'll do it against the same IP address. So here I just want to grab the actual cert using the OpenSSL command line tool, and I'm just going to spit it out to the console, just the serial number. So that's the serial number there. All right, so now what happens when it's time to renew the cert? We do not want to go and restart every app, right? So if I scale this up, kubectl get pods, kubectl scale deployments, and then we'll take the dynamic search deployments, replicas equals, I don't know, 5, who cares? So once we do this, they're all going to just come up and mount that secret and use the same certificate across the board. We don't even need to know what servers they're on. And the nice thing about this is that we do not write these certs to disk on the host. They're all in a temporary file system in memory. The pod goes away, the cert goes away. You don't have to worry about leaving cruft around. All right, so now we get pods, there's 5 of them. Now we need to update certificates, okay? So what I'm gonna do is I'm gonna force a certificate to get recreated. So I'm just gonna delete the object. That's gonna cause a chain reaction to tell Let's Encrypt, I no longer want this cert, invalidate it, also remove it from the system, and if we add it back, we should get a new certificate. So this is gonna simulate an expired cert here. We're not gonna wait 30 days. Okay, that would be too long. So let's delete the certificate object. So kubectl get certificates, and then we'll delete it. So let's do kubectl, I can type, delete certificates, and then we're gonna delete the certificate, okay? So once we delete this, as soon as we do this, that's gonna cause this thing to remove it from upstream. What'd I do?
You said certificates.
Ooh, you guys are paying attention. Most people don't, right? Most people are just like, dude, this talk's too boring. You guys are paying attention, that's great. You guys can get free pizza. All right, so now it's saying, look, the declaration that was keeping this thing alive is gone. So since it's declarative, we're not gonna ask the user to go clean it up. If there's nothing holding it alive, then it should be removed. And this is actually much different than the configuration management tools we use. You ever tried this? You have your configuration management, and then you remove a resource. What do you expect? It to be cleaned up on the other side. Doesn't happen. That's a great indicator that it's not declarative. It's just running scripts with a higher level DSL at the top. This is actually declarative because once we remove the declaration, it goes away. There's nothing for the user to do. If we look at the secret now, it's also gone. There's nothing to clean up here. So now let's put the declaration back, right? So now we're going to simulate that we want, I'm just going to redeclare. We put this back. As soon as we do that, we got to go through the flow. So while we're going through the flow, let's talk about what it takes for the application to actually be smart. This is the thing that kills me so much about the dichotomy between ops and developers. Ops says, look, we're going to build a big machine to reboot certificate or reboot servers when the cert changes. Why are you wasting that much time? It's just way too much time to waste. Don't even build that tool. That tool is quite unnecessary. What we should do is fix the app to teach it how to actually do that. And it's not a lot of lines of code, right? So if we look at this, let's go look at the app really quick and see what it does. So I'm just going to do a code walkthrough while we're getting that certificate. Hopefully it works. All right, so let's go to the entry point for the app. Ignore the flags. I'm going to make this a little bit bigger. So let's take a look here. This is the most important block. I'm going to set up my Hello World server, and in this block, I'm going to give it a special get certificate function, right? So what will happen is every request that comes in, my web server is going to give me a chance to present an SSL certificate. Now, if you're smart, you're not going to load the certificate from disk on every request. That's going to be terrible. So what you want to do is load the certificate in memory. So on boot up, grab the certificate off the file system, store it in memory, and return what you have from memory over and over again, right? The next thing we want to do, though, is some of those patterns we talked about, that watch pattern. So if I look at my certificate manager inside of my app, what this thing will do is if we look at watch certificate function, here I'm just going to watch my file system. So here, where I'm setting up this new watcher, all it is IF notify. So if some of you guys are familiar with Unix, you know that we can actually ask the kernel to give me notifications when certain attributes of a file change. And in this case, we're going to look for these two files, my cert file and my key file. If any of those things change, I want to know about it. And I propagate that up to other parts of my code. So now here, whenever I see that, I will just reload my certificates. And I'll do it in a way that's efficient. So what I'll do here is in my set certificate function, whenever I get the fact that there's a new certificate, I'll load it from the file system here. Once I have it in memory, the new certificate, I'll lock the server so that no one can change the certificate or even ask for one. And I'll unlock it really quick. That's going to take a few nanoseconds. And then the new cert will be served to the next request. All right? And that just happens automatically. No restarting servers here. So let's see what happens. So we're done now. We have our cert. It's back in place. Everything looks good. And now let's check out our app. So we have 5 of those applications, right? And then the goal is that all 5 should actually have the new certificate on their own if that code is actually working. So we say kubectl get pods, and we'll just look at the logs for one of those things. So logs, let's grab this guy, and just see what it says. You can see it. The watcher for the certificate, and then it found it, and it started reloading. So let's verify that by looking at the serial number. So let's do the serial number thing again with OpenSSL. We'll grab the new serial number, and if everything works, that is a new serial number. People are like, no, it's not. So let's just do this and compare. We see that we have a new certificate automatically loaded by every single instance. So if we had 1 million instances running, doesn't matter. Almost in real time, they're going to reload that certificate whenever it gets updated, right? This is what I mean by like the future of ops. It's a very responsive system. It's declarative. You're not pushing ops to the rest of the company. You're just building tools that encapsulate the things that you would do best into the tool itself. And given these kind of abstractions, it's so much easier to deal with. We can go focus on building smarter apps. So that is the certificate manager, and that's a common pattern that I see. You can imagine having tools like this, launch MongoDB, set up a Redis cluster based on your company rules and how you do things. So that's just kind of a high-level tool that you could build using that pattern. So the other thing, right? We have more. So the certificate manager is pretty straightforward, and it gives us a pattern for doing common operational tasks in a way that works in a distributed system, and we can do it in a declarative way. The other thing you're going to do as a sysadmin, I believe, is you're going to have to figure out a way to do more efficient scheduling. Just placing things on nodes based on memory and CPU is not going to be enough, especially because every company is different. So we have this use case. I want to ensure I'm using my resources effectively. I want to prefer machines that cost less per hour, right? So as we start to propagate to the cloud, it can get really expensive if you're wasting CPUs or using the wrong machine. You can imagine some machines in the cluster have a very expensive GPU. The last thing you want to do is run some small web server on that machine, taking up resources where it can't be used for some higher order purpose. So we need to build something a little bit smarter to handle this for us. And if you think about it, we do this all the time in your daily jobs. How do you pick which machine something should run on? You may say, I need to make sure that all copies live in different availability zones. We go through all of these decisions all the time when we're deploying applications. But what we need to do is take those decisions and how we make those decisions and roll them into a tool. More than likely, that tool will be a scheduler. And these things will run side by side. So we're going to build a scheduler now to show how we can start incorporating our own rules and policies. How does the scheduler work? Very similar. Something will create those pods. Either you will or deployment will behind the scenes. And in this case, when we create those controllers and we scale them from 0 to 5 or 3 to 5, they create these pods, right? But as those pods are fed into the system, someone has to schedule them. The default scheduler picks them up normally by doing a watch, just like we saw earlier, on the API server, scans all the nodes, but not by talking to the individual nodes, all the state it needs here, all this global state. We can ask the API server, give me all the nodes, give me all the pods, and figure out how much memory is free on each of those, and figure out which one is the best fit to run our workload. Once we've made that decision, we bind the pod to a node. That's it. Kubernetes makes this super easy because the only abstractions you need to know about is a pod and a binding. How you make your decision is totally up to you. You could totally just do random. Give me a list of nodes and I randomly pick one. Or you can actually go through the fitness functions and I'll show you. So once the workload lands on here, we never talk to the nodes directly from our scheduler. The nodes are just sitting here waiting to say, what should I be running? Right? So let's see what this looks like in action. At a high level, code-wise, you want to schedule a pod. So you get a pod object. The thing you want to do is take that pod and have what we call a fitness function. I'm not going to go into the details of this fitness function, but this function is really simple. Get all the nodes, all the workloads, and figure out how much memory they have free and score them. The ones with the most resources free get a higher score. Okay? That will be our first fitness function. And this is what the Kubernetes scheduler does by default, right? But what happens if you want to have the best price? Well, that's totally custom. That's your world. Kubernetes doesn't know anything about this. So we add a new function called best price. We take the nodes that we get out of the first fitness function, meaning that that list of nodes, one or more, has the ability to fit the workload based on memory and CPU. But in terms of price, we're going to have our own fitness function. So this fitness function will take that list of nodes and sort them based on price. The one with the lower price gets to run the workload. And then we'll just bind the pod to that node that comes out of that, right? That's the most basic scheduling algorithm, right? And I think a lot of people will be writing a ton of these, right? There's going to be other reasons, like approvals. Like we can't deploy this app unless it's approved by this particular team. Where do you put those rules? No one scheduler will rule them all, and most organizations that are using these patterns have lots of schedulers, trust me. So let's go through this, and then we're also going to do the watch pattern. We're not going to be doing a loop by default looking for these things, so very similar pattern that we saw before. Watch for unscheduled pods. And then here's what my reconciliation loop looks like, right? We have this interval, and then we'll make sure that we have everything scheduled in the system. So we're going to do the scheduler demo really quick. This will be much shorter. So we're going to run some workloads. I'm going to show you how to do that in Kubernetes. How do you run multiple schedulers in a system like this? All right, so the first thing we need to do is we need some workloads. So let's see what we currently have in the system. Get pods. I'm going to remove this so we can have a little bit of clarity. So dynamic search, I'm going to delete that because we don't need that right now. So I'm going to delete that deployment. And we're going to delete the deployment for dynamic certs. All right, I don't need it in the system. So that's going to automatically clean up all the pods that are created and leave the secrets in place because it doesn't own that. All right, so now we need a new workload. I need a workload that can only be scheduled by my scheduler. All right, so there's a couple of things you need to do in Kubernetes to make this work. So this workload, so this is a deployment like we saw earlier. The important bit that I want to highlight here is this annotation. This annotation tells Kubernetes that this can only be scheduled. Well, really, it only says the default scheduler shouldn't touch this. The scheduler running in Kubernetes should ignore this particular workload. or anything created by this particular deployment. So if we scale from 1 to 10, none of them will ever be touched by the default scheduler. So here's a template. Every pod that this deployment spits out will have this annotation in place. The default scheduler will ignore it. That means you have to deal with that with yourself. The other thing that's important here is the resources. What I'm saying here is half a CPU, 64 megs of RAM, right? The nodes are only so big. Right now, each of these nodes have 8 CPUs. So that means if nothing else is running on them, we should be able to get 16 of these per server, right? Now, to make this work, we also need the annotations. So I'm going to show you what the annotations look like. So for each of my nodes, these are my node names. You see how I'm assigning price here. I'm starting with 5 cents and doubling the price as we go up, right? So I'll say kubectl get nodes. Here's all the nodes in the system. I'm going to run this command basically calling kubectl 5 times, and that's going to give each of these nodes an annotation. So I'm going to cost 5 cents, 10 cents, 20 cents, 40 cents, 80 cents. Right? So that's enough information now that our scheduler can use to make decisions. So let's just do that now. So bash annotate all the nodes. So now that we're all labeling them based on price, you can imagine getting this label from, syncing this up with your cloud provider. If you know how much things cost, people spin them up. You give that an annotation so people can use that in the system. And remember, these things can be added dynamically. The price may go up for a server. Maybe it's deprecated and they're going to charge you more. You can change this on the fly. Now, once we have this in place, let's run that workload. kubectl create -f deployments, and then we'll just do nginx. So at this point, we have the nginx deployment in place, and then we're just going to do a watch here. Notice it's pending. How long will it pend? Forever. As long as the system's up, this will pend forever. And this is what you want, actually. Imagine doing maintenance on your scheduler. You don't want that thing to have an error. That's not an error. Just because there's no scheduler to schedule it does not mean an error. It just means that the declared state says we want at least one of these running, but no one has assigned it to any node. So we need a scheduler. So what I'm going to do is show you how you can actually build a scheduler. Actually, I won't walk through all the code. I don't have enough time for that. But here's all the code for it. It's on GitHub. I'll share links. So this is just written in Golang. This is on my local laptop. And this is how I build these actual tools. So from my local laptop, what I'll do is I'll start what we call the Coop Proxy. The nice thing is this is my Kubernetes command line tool. It knows how to authenticate the Kubernetes. It has all the credentials. It knows where the master is. It's already configured. And it will just give me a reverse proxy so I can talk to the Kubernetes API right here on localhost. And also so you guys can't hack me, right? So people do that at conference talks. I don't know why. So here we have this IP address. So what I'm going to do is I'm going to take my scheduler. I'm going to run it from my laptop and try to schedule that workload, all right? So we got to build it first. So go build. I'm just going to compile my scheduler. It's done now. It's fast, isn't it? Like, wow, that was quick. It's awesome. All right, so we have the scheduler. So I'm going to run the scheduler now. So the scheduler's starting, and it's going to come up and reconcile the system and says, hey, I found an unscheduled pod, and I'm going to assign it to a node. Look at the node it assigned it to, 2KWA. Why did it do that? Why? It's the cheapest. So if we remember, if we look at this thing again, if you look at the annotation, you see the pricing order, right? But what happens if the cheapest server fills up and there's no more room for CPU and memory? What should happen? It should go to the next one, the next cheapest. And this is what we call bin packing by default. So this idea that we're going to fill up the cheapest server first before we go to the next is bin packing. And most of these tools do this by default. So let's see what this looks like in action before we wrap it up. So I need more. So how do I fill up a server? Well, we know that half a CPU, each of these things costs. And I have 8 cores on each of these machines. So how many pods do I need? 16. Some of you have been out of math class a little too long. It's like, damn, that's a hard one. 8 times, is it times? So funny. All right, so here's the pods. We have 1. So we need how many more? This guy in math. 15. So we just do a little bit more just to make sure that we fill it up. So here's what we're going to do. We're going to watch our scheduler. Actually, let's deploy our scheduler. Let's actually run it in a cluster. Like running from my laptop is not a smart idea. So any thoughts on how I'm going to get this scheduler into the Kubernetes cluster? You need a Docker image. You get bonus on that, yes. But we need to make a deployment for it. So I need to deploy my scheduler, actually. So here's my scheduler. I'm going to do it with a deployment. But it also needs to be scheduled. Right? It needs to run somewhere it can actually run. How does it get scheduled? The default scheduler, yeah, that thing. This guy's paying attention. I love it. So I'm going to create this scheduler. So now our scheduler is running inside of Kubernetes. Right? So this should give you an idea that there can be multiple schedulers in Kubernetes, and it's actually encouraged. So we'll run the scheduler, and it actually also has this Coop Proxy built in. So I'm going to turn this off. I don't need my local machine anymore. So now that our scheduler is running, I'm going to tell its logs so we can see what's going on. So kubectl logs-f, let's grab this thing. And we want to get the scheduler containers logs, so not Coop Proxy. All right. So this thing ran into an issue where the proxy wasn't up first. It came up. Now it's good. All right. So now our scheduler is up and running. Please be up and running. So now let's scale those pods. So now what we need to do is get, you guys said 15 more. I'm going to do a little bit more than that. So scale, deployment, Nginx, and then we'll just do, I'll just say 20, right? Look at what our scheduler is doing here. So it's continuously placing the new pods on the same server. This is what we expect because we still have memory and CPU free. It's going to keep doing that because that's still the cheapest server. Right? If I were fast enough and I created a new node that was cheaper, then that node would win because of the way that we're doing our scheduling. So we're going to do this until we run out of space on the first node. And then if this thing is working, it should pick the second node that's the cheapest. So 51JU. So let's verify really quick that that actually works. So cat annotations, and we see here 51JU is the next cheapest server. And it's going to do that continuously until it works. Now, if we were to kill this particular node, well, it just has to move all of our workloads. I'm going to be ambitious and just try that. I don't know if this is a smart idea because I didn't plan for that. And we're going to wrap with that if that works. So we're done scheduling everything. So let's see what happens now. So kubectl get pods. So these things are all running now, right? Like a badass, all your apps are running. Now, what happens if we delete the cheapest machine? What do you expect to happen? So the deployment is going to pick that up and notice that we're not meeting the definition of the cluster. The scheduler is still not in the loop yet. Then the deployment will say, hey, I got to go and create 15 more of these things and put them into the API server. The scheduler will then be watching and go through its loop again because there's no guarantee that the cheapest server was even there. We can't assume anything in these systems. Well, let's try to do that now. So let's say get nodes, kubectl, get nodes. Let's just make sure that we know -o that this thing was running on a specific node. I'm going to make this a little bit smaller. Sorry if you can't see it. But we see here that this node that everything is on is that node right there. Right? So we're going to grab that node out. And what we're going to do is now is going to simulate a failure. Actually, we're just going to tell it that it can't be running anything else. So kubectl, there's a command here that does this. So we're going to drain that machine, meaning we're going to take it out for maintenance. Now, we could be a little bit more brutal and just like unplug it, but it takes 15 seconds for the system to, or maybe longer depending on our configuration. So we're going to say drain. So kubectl drain, I think it's node. So we want to drain our node. So let's do drain our node, and we're going to give it that node. Okay. So let's look at the scheduler really quick to make sure that we can see what it's doing. Right. So it's done all its work. There's nothing else to schedule. Everything is running. So now we're going to pull the plug on this guy. Right. So now the node itself is being told that, you know what, everything needs to abandon ship and get off of it. It's letting me know that, oh, I need to force it because there are some daemon set things there. I don't care. So daemon sets are like my logging services, all those things. So what will happen is, once that happens, my controller will pick up that you don't have them all running, right? So we'll get rid of this. This is just showing me on my pods. So if I say get pods, we'll see that some of them are terminating now, some of them are pending, because they all had to move to the next server that's available. We don't have all servers anymore. So if you notice now, Oh, I think I actually brought it back online. That kind of sucked. But you see 5Js coming here. Oh, why did it come back online? You're not supposed to do that in demo. Kill it. You know what? Let's do it. I don't know how long it's going to take, but let's do it. All right, we're going to delete the node because this guy thinks that's a good idea. If you're hiring, probably not that guy.
Unless you're hiring for angry mob leaders.
That's funny. That's real funny. The other thing we also do in Kubernetes, so I'm going to delete that VM. I'm also going to delete the node as well. Okay, so that's gone. This VM is gone. This just doesn't feel like a good idea. But you know what? It's a meetup. We're doing it live, baby. Come on. So at some point that will complete. And what is our scheduler's over here freaking out now? Like, what the hell are you doing? Why are you listening to that guy? But you notice it's working now. You notice it's working now. And this is the kind of system that you want. And with that, I'll end the presentation. Thank you.
We do have some time for some questions, so if anybody has questions for Kelsey,
And those hands went up quick, man. I'm going to make you go second. I'm just joking. Good question. So the question was, why do I have kubectl pod running next to my scheduler? I encourage most people when you're starting to build tools like this, do not try to encumber yourselves with how to do authentication through the Kubernetes API. It's actually pretty complicated. We have like this kube config file, some service tokens. You need to know where to look. You could teach your application to do it. So one way you can cheat is by having the kubectl run in proxy mode. So in Kubernetes, we have what we call a default service account. And you can make others. So when you run kubectl in your pod, it will actually, Kubernetes, when it launches pods, it will inject the credentials for apps that do service account stuff. And then kubectl will read that, connect to your API server. And then all you have to do from your app is assume localhost, right? And it makes it really easy to build these things. And actually, I'm not even using the Kubernetes API. If you look at the code that's on GitHub, you'll see that I'm actually doing this in the way where I'm just using HTTPS. So if I go to my scheduler, if you look at my scheduler and you look at like my Kubernetes integration, I'm just using the HTTP REST API. I'm creating the HTTP client. I'll show you here. I'll show you like the binding code, for example. So down here, where I want to bind my pod to a node, I'm just creating an object here. I'm going to turn it into JSON here, put it in the body, create an HTTP client, and just do a post, right? And now I'm assuming that all I need to do is talk to localhost. So I just run the proxy to make my life super easy. Works on my laptop, works in the pod. Good question, by the way. Any more questions? You guys just understood all that stuff. I knew it was too easy. Damn it. Was this helpful?
Yeah, no, it was an awesome presentation.
Are you going to go home and like,
Yeah.
Yep. Make sure you tweet that. Make sure you tweet that.
So often companies would like to segregate their customer data for security reasons, like in medical records. Do you see a scheduler being set up that level of implementing a business policy? It's not really how you would do it if you had no criteria, but maybe you need very clear logical separation.
So the question was, could a scheduler help enforce business policies like HIPAA data, PCI data, where this workload can't run on this node? And we actually have something like that. It's called affinity. So you want anti-affinity. So you could imagine a world where you say, you know what, I will never run the Kubernetes default scheduler. Just turn off the binary. Just off. It will never run in my system. And then what you would do is you would have your own schedulers that enforce this kind of thing. So when people schedule workloads and you don't see an annotation for a schedule that's approved, delete the pod. Nope, that's not allowed in my system. And then you can have your own rules to say, this server, so you may add annotations like this server has PCI data on it. There will be no pod ever allowed to be there. So you may do your predicate scan and it comes back and you may say, yeah, those things have PCI, remove them from the list. If there's nothing else If there's nothing left after that, then you throw it away. In Kubernetes, we also have what we call node selectors. But that requires a little bit of trust from people creating the workload. So this is why a lot of times, instead of me doing those commands, I create the YAML definitions. And you can actually have a node selector to say, this must run on a system that's PCI compliant. So then when it's given to the scheduler, and the scheduler, the default scheduler, respects those predicates. So it looks at the node selector and starts to filter nodes out even further based on that. But you see this in a lot of the enterprise-grade schedulers, actually. This is mainly what they do. If you think about a cloud provider, this is what we do at VMs, right? We know that some customers have rules that this customer can never run on those hypervisors, like if you're in GovCloud, right? That's how you do things like that. So schedulers are definitely the right way to think about it. It's not all about speed and algorithms. Sometimes it's about policy and control. Good question.
Do you have any overhead for the system for running Kubernetes on all of your nodes? Is there any overhead?
All right, so the question was, is there any overhead for running Kubernetes on all the nodes? Yes. Breathing has overhead, right? If you look at your server and you're breathing on it, you're probably doing something to the server, right? So the overhead for Kubernetes has a cost. So all of our components are written in Golang. This is kind of important. If you look at the kubelet, it's probably using 15 to 20 megs of RAM, okay? We account for all usage. So if you want to see what that usage looks like, you can actually go kubectl, get nodes, right? So we also have like logging agents, proxies, all these things, right? So we have pods for all of them so we can actually keep a track of the resource usage, right? So we say kubectl, describe nodes, and we'll describe this node. I think this should work. So if you notice here, this is all the things on the system being used, okay? So we have this fluid logging thing. We have a proxy server. We have some other things running on there, not a lot on this machine. We see the resources being used. Not everything's using all of its resources. So some things were allocated X amount of memory, but it's not using very much. So this thing isn't overcommitted. So most of the components that run there, we normally don't take up too much other than, you know, there's a process listening to the API server. And it talks to, like, in our case, Docker for this particular demo. And then Docker takes up its resources. But other than that, you're just in container world. So when people go out to build these things in production, and you think about the VM model where you're making these VMs like 2 gig, 3 gig, and then you're auto-scaling to like 500 of them. In this world, you would make the VMs a little bit bigger, right? Or do bare metal. And then let Kubernetes carve up the resources. So you're not going to actually have an OS per app anymore. A lot of people do that in the cloud, right? You take a whole VM, you put one app in there, and you auto-scale it. But you're wasting 200, 500 megs of RAM for the OS, and God knows what for the CPU, because you can only buy in certain increment sizes. But in this world, since you're going back down to the container, you can get a lot more granular. You saw when I did the Nginx thing here, that we were very fine-grained on exactly what the application needs. And actually in Kubernetes, we're working on a thing that will actually bump this down. So if you ask for 500 megs, we actually get the real-time data of actual usage. So if you said 500, and for 3 months you've only been using 200 megs of RAM, we can suggest to you that you should go from 500 to 200. We recently did this with our VM. So if you log in your Google Cloud Console, you look at your VM, we say it's too big. You've never, ever used it all. You should probably save yourself some money and get a smaller one. And we're going to do the same thing inside of Kubernetes where we will say, and you can have a policy that you just bump this down automatically. So if you're only using 200 and you specify 500, we can rewrite it to 300 and then see what happens, and then we can bump it up. So the overhead for these things is actually way less than having one VM per application, but you do have to have some cost for agents to be running, almost equivalent to like a monitoring agent on the server. Okay? Good question. Any more questions? Maybe one more? Dan?
Is there any labels?
All right, so the question was, are there any labels or support for what we call oversubscription or best effort? So once you really get these things to be super powerful, the ability to oversubscribe them is where the power comes in. Like for every cloud provider, you oversubscribe to hypervisors, how you get as much money as possible, because most people do not use all the resources when you allocate them a VM. We would like to see the same support in Kubernetes, but it's actually really hard. It's really, really hard, and it's a whole talk on its own. In order to do that, we need to actually add priorities to the system. So imagine having n number of servers, and you fill them up, okay? And a server dies. Now, you've never changed the declaration that these things need to be running. Who gets kicked off the server and who doesn't? You need a priority system to be able to say who goes first, right? So until that's done, actually some of that code is checked in, but it's not done yet. But the whole system actually has to understand this idea of priorities and be able to overcommit the system. We think we might be able to do it for like CPU, memory is actually super hard. Everyone thinks they can do it from memory, and it actually doesn't work. Like every time I've seen a system like that, it's like, oh, you can do it from memory. Memory is very complicated, right? How much is actually being used versus cached? And if you oversubscribe memory, your apps start doing really weird things. So everyone asks for that feature, but I think it's one of those things that are super hard because when an app does need all this memory and you've oversubscribed memory and mallocs start to fail, that's going to be terrible, right? So I think there's a lot of thought that needs to be put in it. This is why we're not racing to do it, even though we do it internally in Google, right? We just know that people need to be very careful when they do it in a system like this and they don't understand what they're getting themselves into. Thank you for all your questions. I'll be around a little bit afterwards. Thank you.